We got to the types of chemical bonds such as ionic bonds.
We did already talk about ionic bonds, or we had not yet?
We had already talked about them.
Okay, so that means all we have left are the hydrogen bonds. So we talked about the covalent bonds. There was two types. What were the two types of covalent bonds? Polar and nonpolar. I guess first review question would be, what makes a bond a covalent bond?
The physical sharing between electrons.
Of the electrons. Yes, for it to be a covalent bond, the electrons have to be physically shared between elements. And what's the difference between polar and nonpolar?
Polar is unequally sharing and non-polar is equally sharing electrons.
Yes, so polar is your unequal sharing of electrons, and nonpolar means that the electrons are being shared equally. What does it mean that the electrons are being shared equally? What does that mean?
The time that they're orbiting around the element.
Is what?
equal.
What about the time? Is it different
They
amounts of
spend
time?
equal time.
Equal amounts of time, right? So what it means that electrons are being shared equally is that the electrons orbiting these elements that are part of this molecule, the electrons will spend equal amounts of time orbiting both of those elements, or three or five of them. Okay? Then we had the ionic bonds. The covalent bonds were our strongest, and the ionic bonds are a step below. They're not as strong as the covalent, but they're stronger than our third bond, the hydrogen bond. If you were to describe to me what causes an ionic bond, what would you say?
Can you repeat the question?
They steal an electron to fill an outer shell because it's stronger.
Yeah,
they
yes,
still-
yes, that is what happens, right? So the bond, how you get the ionic bond is you have a transfer of electrons between two elements. So instead of the physical sharing, you have a transfer. Somebody gains electrons, somebody loses electrons. It can be one, it can be many, but you have an exchange there. I called it stealing, didn't I? I said somebody's stealing from somebody. Same thing, somebody's gaining, somebody's losing, there's a transfer. That transfer creates a charge. The transfer of electrons creates a charge on those elements. And those charges will be opposite. One will be positive, one will be negative, and the opposite charges attract, right? That attraction between those two charged elements, or those two charged atoms, that attraction is the ionic bond. So the ionic bond is the result of electrons being transferred. The attraction part is the actual bond. Do y'all see why that's weaker, right? Because it's not a physical sharing. So we did table salt as an example of that. If we're good with those two bond types, let's move on to our third one, which was our weakest of the three, the hydrogen bond. Hydrogen bond is probably the easiest one to identify because hydrogen has to be one of the elements. The difference here, the hydrogen bond is a bond between hydrogen and another element on another molecule, and it's a attraction bond between positive and negative charges. Hydrogen has to be one of the bonds, and it's an attraction bond. Usually you find this between polar molecules because your polar compounds, right, they have a positive area and a negative area, they're charged. Hydrogen is usually part of that, and hydrogen will usually have the positive charge. That positive charge on that hydrogen will be attracted to the negative charge on a different molecule somewhere. In this case, they're showing water molecules, how they interact with each other so that you get flowing liquid water, right? There's bonds between them, hydrogen bonds. How is this different than an ionic bond, which is also an attraction bond between positive and negative charges? How is this different?
They have the same charges instead of opposite.
No, these are opposite, right? Positive here to the negative side of the oxygen.
Is it because
What caused that bond?
The attraction of negative and positive?
Do what?
The attraction?
the polarity?
So with our ionic bond, what caused the positive and negative charges was there was an exchange of electrons. What causes the positive and negative charges on these water molecules?
The polarity.
The polarity, right? Which is the result of the electrons not being shared equally. It's not because somebody stole from somebody or there was an exchange. This attraction bond is the result of polarity, is the result of electrons being shared unequally. That's the difference between the two bond types, because they both are an attraction bond, but that's the difference. And hydrogen, right? Hydrogen has to be one of the players. So let me stop here on water, because a good chunk of chapter 2, this next section, has to do with the properties of water. Because whether you're talking about people or you're talking about microbes, water is one of the main supporting molecules of life. Every living thing that we know of at this point requires water in some way. So water is very important. And a lot of the properties that support life we get from water being a polar compound. Its polarity gives us those properties. So look at this image here. This is water molecules interacting with each other, and this is what they do. So picture liquid water. You've got a lake, a pond, a puddle. You got a very fluid body of water in front of you. These water molecules, as a positive area of one gets next to a negative area of another, will form that hydrogen bond with each other. This is another example of how the books kind of just don't have a good way to show what really happens here. These hydrogen bonds between these water molecules are not set. So this water molecule here does not form a hydrogen bond with this water molecule and they're forever bonded. It's a very weak bond, and these bonds between water molecules last a trillionth of a second, right? Water is very fluid, it's constantly moving. Even stagnant water is moving. And it's because these water molecules are constantly moving. And so these bonds last a trillionth of a second. This water molecule will get close to this one, bond for a moment, and then it'll rotate off and get close to this one over here and bond for a moment. This one will rotate back, and you'll find areas congregated of water molecules congregated in an area here, and there'll be a gap here and a bunch of them here. There's no pattern to it.
So it's unstable, in other words?
It's not unstable. The water molecules, they're just not in a structure. They're not in a pattern. They just float wherever they want, and they're constantly exchanging bonds. But water's not unstable. Water's very stable. Now, so you're picturing your body of water. As that body of water, the sun shines on it. So as those water molecules get heated, they absorb energy. That's what they're really doing. Right? When something heats up, it's absorbing energy. What happens to kids? Anything. What happens when something gets energized? What happens?
Moves faster.
They move faster, right? They move faster. Same thing with your water molecules. When they get energized, they start to move faster. And they eventually move so fast that they can no longer form these hydrogen bonds with each other, and that's when you've gone from a liquid to a gas, when they do that. Now let's do the opposite. Let's say that they start releasing energy, which we commonly call cooling, but in science, cooling is not a real word, right? They're releasing their energy. So as they cool off, what they'll do is they start to slow down. And they will eventually stop moving. They'll release enough energy that they don't have any energy to keep moving. And these bonds will freeze, right? You get ice at that point. You've gone from a liquid to a solid. Not only do those bonds set, but the water molecules spread out. You don't have some closer together, some further apart, a group over here. They all get equal distant apart, and they take this very structured configuration. They spread out. Y'all ever taken like a Coke can and put it in the freezer? What happens to it?
Explodes.
It expands, and sometimes it explodes. Yeah. What have the water molecules done as they froze? They've spread out. And that takes up more room in the can. Well, the can's only so big, so it pops. Water running through a rock, if that water running through the rock freezes, what does it do? It expands and it busts the boulder. So you have water will bust huge boulders doing that. This is something that's sometimes hard to visualize, so I have a visual for y'all.
Do you have that PowerPoint in our notes?
This one is a biology PowerPoint that I have a link in I'm trying to get. But the one I've been teaching y'all from right now, yes, it's on Blackboard. Did I already show you this? The water moving around?
Not this particular one, no.
We don't need this now. Okay. So, liquid water. Now they slowed this way down. Remember, these bonds last a trillionth of a second. But do you see how that they're just constantly moving, and you've got some over here and some over there, and there's a gap, and there's no real structure. They're just, it's liquid, it's fluid. They're moving around. They slowed it way down. The bonds normally only last a trillionth of a second. They're hydrogen bound, hydrogen bonds, very weak. A little water bug runs across there, and the bonds don't break. But what happens if we step on liquid water? We go right through it, right? We break the bonds. As those water molecules release energy, they will eventually stop moving and they spread out when they do that. Do y'all see how structured solid ice is compared to liquid water? Where's my count that? Right there. Do y'all see how structured that is? They're all equal distance apart, and they're not changing their bonds. So the water molecules have spread out. Think about this. Water can be found in all three states of matter, right? Three states of matter are solid, liquid, gas. Water is one of the few. You can find it in all three states, a solid, a liquid, and a gas. Not many things do that. Water also is one of the few compounds that you can take its solid version, put it in its liquid form, and it will float. Most things, when you take them from their liquid form to their solid form and then put them in their liquid self, they're going to sink. Water is one of the few that will float when you do that. Why? Why does it float?
Because of the polarity of the bonds are keeping it.
True, yes. We're not seeing any changing in the bond. But the water molecules have spread out here. So if I were to take a cubic foot of ice and count how many water molecules are inside it, and then a cubic foot of liquid water and count how many water molecules are inside it, which one would have more water molecules in it? The liquid or the solid? The liquid would, right? Because they're crammed together, they're not equal distance apart, they didn't spread out, they're all crammed in there. And then what would happen if I froze that liquid water? They'd expand, and they would then take up more room than what that bucket I have them in is. So if you took a cubic foot of already made ice, they've expanded and spread out. So there's fewer of them in that set area than if you took a cubic foot of liquid water, because they spread out. They're taking up more room, but there's fewer of them because they spread out. Does that make sense? So it's kind of like our coronavirus quarantine procedures, right? We could have, if you were to fill a stadium with people, one person in every seat, that's quite a bit more people than if you put a person every 6 feet apart. You're still taking up overall the same amount of space. You're still utilizing the space at the stadium, but everybody's more spread out. And so there's fewer people in there taking up the same amount of space. Does that make sense? This is why ice floats. The technical term for this is that ice is less dense than liquid water, which is why ice floats. Something that has a lower density is going to float in something that is more dense. Holds it up, right? This is great for our microbes because this is what preserves our microbial life in our water systems. In which we think, well, why would we want to preserve microbial life? Well, I know we focus on the microbes that make people sick, but that's a small drop of the microbes across the planet. Most of them are very beneficial, and most of them don't bother us, and we actually need them around. And the ones in our water systems have a purpose. They have a role in life. We kind of get upset when we take over an area or invade a tropical rainforest, and then we get sick from something we've come across in there. It's just in there doing its thing, and we get so upset. But of course we are. We don't want to be sick. Very few of the microbes you took a total count actually make us sick. Most of them are harmless. And so, yes, they need to be preserved. ice floating is one of the ways that happens in our water systems. Think if ice didn't float, what would happen during winter? So we're picturing winter here. I can remember as a child the pond freezing over a couple of times throughout my childhood where I got to walk on it. But for the most part, there was a layer of ice and then there was liquid water underneath. Picture more of the Arctic and Antarctic regions and the really cold places that have dozens of feet of thickness of ice on their water systems. If a layer of ice formed and then it sank, and you're back to liquid water on top, another layer formed and then it sank, another layer formed and then it sank, what would eventually happen?
You'd have no water.
You'd have no water. It would freeze solid, and all the life in there would be frozen as well. Some of it would die, some of it wouldn't, but it would completely destroy that ecosystem that's in there. Now, like I said, we've had occasions where our ponds have frozen solid because they're so shallow. But the large bodies of water, the ice floating acts as an insulative barrier and keeps the depths from freezing solid and preserves that life in there. Okay. Okay, hydrogen bond. Are we good with the hydrogen bond? It's our weakest. Do you see why it's the weakest? So it's still an attraction bond. Obviously it's weaker than the covalent because it's not the physical sharing. But because hydrogen is always one of the elements in the hydrogen bond, how weak is hydrogen? It's the weakest, right? It has very little ability to pull on anything. And so when it's the one that's causing the bond here, that bond's going to be very weak. Where we're going to see the hydrogen bond going forward is mainly in our discussion with DNA. So I know we're not focusing on people, but microbial DNA is a big topic because we try to target different things about their DNA, learn about their DNA, prevent them from mutating their DNA. We work a lot with their DNA. DNA is a double-stranded helix. What holds the two strands together are hydrogen bonds. So if you can break those, then you can damage that DNA, which is what the radioactive isotopes do. If you get radioactive isotopes in your DNA, they break those hydrogen bonds and separate the strand. Your body's pretty good at putting it back together, but every now and then there's a mistake. Okay. All right. This is more of, we're getting into a completely different set of foundational piece we need here. So it's kind of seems like it's random bits, but it's all things that you're going to need or that you're going to see through this class going forward. Redox reactions are something that come up because we do study the metabolism of microbes during this class. And it applies to humans as well. So I think we talked about that very first week of class, that we do the metabolism section, and it applies to both. Everything's got to metabolize. That's part of what makes something living, is that it metabolizes. Things that don't metabolize, we call them rocks and things like that, and they're not living. And so when we study metabolism, one of the things that's going to come up are the redox reactions, because that's what metabolism is. It's a bunch of reactions. If you had biology, we talked about this in there. If you had A&P, I know the redox reactions are part of that discussion as well. So mainly it's just keeping your terminology straight, because we've already looked at something that loses electrons and something that gains electrons, right, with our ionic bonds. We saw table salt as our example. Sodium and chlorine exchange electrons. Somebody gains, somebody loses. There are terms associated with that when that happens. There's a correct terminology and a correct way to say that that's occurring. Oxidation is referring to whoever loses the electron. So the loss of an electron, that means that that thing is being oxidized. If something gains an electron, we call that a reduction. You think, well, how is a gain a reduction? That seems backwards from what I think it should be. Seems like whatever's gaining should be oxidized and whatever's losing should be a reduction. Well, why we call a gain of electrons a reduction is because when you gain a negative charge, you're reducing your charge. That's why gaining electrons is called a reduction, because you're reducing your overall charge. Is it possible to have somebody lose electrons and not have somebody gain electrons? No, it's not possible, right? If somebody loses, that means somebody gained one. The only reason somebody lost one is because somebody gained one. You cannot have one without the other. And so a lot of times, instead of saying, well, there was an oxidation and a reduction reaction, you just say a redox reaction. It's a summation of these two, because you can't have one without the other. If somebody gained, it's because somebody lost. And if somebody lost, it's because somebody gained. Now, look down here, because this is the part that sometimes gets confusing for all of us. Sodium, chloride. Y'all know what happens here, right? This is the ionic bond. Chlorine steals an electron from sodium, so there's an exchange here. Chlorine gains an electron, sodium lost an electron. Without looking at what's being talked about in the bottom, because that's referring to something else. Who was being oxidized? Sodium or chlorine? Sodium, because oxidizing means that you've lost an electron. So if sodium was oxidized, what was chlorine being? What was happened to chlorine?
Reduction.
Yeah, chlorine was reduced. So notice they have said that sodium is the reducing agent. Well, we just said that sodium was oxidized. Well, why they say that sodium is a reducing agent is because sodium caused chlorine to be reduced. Sodium was oxidized. It was oxidized by chlorine. So chlorine is the oxidizing agent. Chlorine itself was reduced, but it oxidized sodium. That's why they, and those are confusing, right? Because you want to say, well, no, sodium was oxidized. It's the oxidizing agent. What this means is that sodium caused chlorine to be reduced. Chlorine caused sodium to be oxidized. Make sense? Again, that's just keeping terminology straight. It's silly, isn't it? Yeah. Okay, chemical shorthand is something else that we'll use in this class. And we've used it already. We've used sodium chloride for table salt. We've used H2O for water. We've already been using it. It's part of something that we're kind of just taught as we grow up. So a lot of this already looks familiar. Y'all know what reactants are. It's whatever's required for the reaction to happen. And the products are whatever's made from the reaction after it happens. Usually what they tell y'all is that the reactants are on the left side of the equation and the products are on the right, right? There's several different types that we'll see this semester. One is a synthesis reaction. And if you read the definition, it says the reactants bond together in a manner that produces an entirely new molecule. Seems pretty obvious, right? You stick them together and they make something. The example that your book gives you is sulfur with oxygen gas. This one is a very simple synthesis reaction. They're not all this simple. But you take a sulfur, an oxygen molecule, right, oxygen gas, put them together, and you get sulfur dioxide. This is smog. That's what this is, smog. They're not all that simple. Take water. You would think the formation of water would be very simple. It's 2 hydrogens and 1 oxygen. But does oxygen exist by itself like that? No, right? Oxygen, you find it bound to things. Most commonly oxygen gas. So water, for example, it takes 2 hydrogen ions and 1 O2 to get water. So 2 of these H2s and 1 of these oxygens, and then 2 of these H2s and the other oxygen. So it ends up giving you 2 water molecules. It's still pretty simple, right? You're just rearranging them. But you have to have more than just 1 of each because of the way oxygen is found in the environment. So this is a synthesis reaction. You took 2 separate things, you put them together, and you got water from that. But they're not all as simple as the example that your book gives you. The decomposition reaction is exactly what it sounds like. It's the opposite of synthesis. So instead of putting together, you're taking apart. So here's water breaking back down. 2 water molecules. I did do that wrong, didn't I? No. Yeah. Yeah. 2 H2O2s gives you 2 water molecules and oxygen gas. That would be an example of the way that this could break down. We see this. No, I did that right. I did that right. Ignore me. That's hydrogen peroxide. This is water here. This is a decomposition reaction that we'll use a lot in this class. This is hydrogen peroxide being broken down into water and oxygen gas. I think I talked to you about this already with your staph and your strep. So as we work with staph and strep, as we culture it, as we stain it, as we're working with it, they look the same when you grow them. They're both white colonies for the most part, the ones that we have in the lab. There are different strains that some will colonize pink, but the ones we work with are all white. And so they're also both gram-positive. And so if you're trying to pick them out, they look the same and they test the same, but they do have one difference. Staph has a catalase enzyme and strep does not. But what a catalase enzyme is it's the one that causes this reaction. A catalase enzyme will take hydrogen peroxide and break it down into water and oxygen gas. So there's an enzyme that makes this reaction happen. Well, if you want to know if what you have is staph or strep, you can take a drop of hydrogen peroxide and put it on your growth, your colony of growth. If it's staph, which would have the catalase enzyme, you will see that hydrogen peroxide being broken down into water and oxygen. We'll actually only see the oxygen, we'll see bubbling. But if it's strep, you put that hydrogen peroxide on there, they don't have the catalase enzyme and nothing. You have hydrogen peroxide sitting on your colony, it does nothing. And then you have the exchange reaction, where they basically trade with each other. So this is a good example, and I'll leave this one on here because we do work with acids and bases. Your microbes are very sensitive to pH. Whether we're talking about botulism and how it forms in canned goods, or we're talking about the pH in our body and how that supports microbial growth, or for example with us, your blood pH. What's your blood pH supposed to be? Do you remember? 7, specifically 7.35 to 7.45, right? There's a very small range there. Pretty close to neutral. What about the pH of your stomach? Is it different? How different? Is it pretty acidic? Yeah, much more acidic than the pH of your blood. So the microbes that would infect your blood are a completely different type of microbe that would infect your GI tract. Because the ones in your blood like a pretty neutral pH. The ones in your GI tract are going to be the ones that are able to survive in really acidic environments. Usually they're also the ones that don't need oxygen because there's not any oxygen down in your gut. And whereas your blood is full of oxygen, right? So different microbes like different environments, and you can tell where one's going to show up. And then if one gets somewhere where it's not supposed to be, sometimes it's a different problem. So what this is hydrochloric acid, which is an acid, sodium hydroxide, which is a base. If you take them and combine them together, look at how it just gets rearranged. The sodium off the sodium hydroxide, the chlorine off the hydrochloric acid come together and make table salt, right? Who knew you could take an acid and a base and get table salt with a byproduct of water? So that would be an example of an exchange reaction. Another point to make with all of these reactions is that they're a summary. They are a summary. You don't really just take hydrochloric acid and sodium hydroxide, put them together in a jar, shake them up, and get table salt and water from that. That's not really what happens. There's a temperature you have to apply. There are several different enzymes, and there's about 10 more reactions in between what you're seeing here to make that happen. So these are actually just summaries, right? They show you what you start with, they show you what you end with, but not necessarily give you the whole picture. One way, especially in chemistry, and I think on your T's they have you do this, they have you check to see if an equation is balanced. And what that means is if you count how many of each of these things are on the left side, you should have the same number of these things on the right side. Because we don't create matter, we don't destroy matter, we just rearrange it, right? Nothing, during a reaction, nothing is created or destroyed, it's just rearranged. So, for example, if you count how many hydrogens, we have one hydrogen here, we have a second hydrogen here. You go over to the product side and you count how many hydrogens. I have 2 there, nothing else. So are my numbers matching up? 2 and 2. Same with all these others. If you went through and counted, they would all match. You're balanced. If they don't match, that means the math was wrong, right? You did something wrong with the math. We don't do any of that in here, but I know that shows up on your T's, so make the math match. Okay, this is something else that we get from water having polarity right here. So solution, solute, solvent, those are terms that we throw around just in general science talk. They actually do have some meaning. For something to be considered a solution, you've got to have at least 2 things in there. You can't just have a beaker of water and that be a solution, right? It's just water. If you want it to be a solution, it's got to have at least 2 of something in there or more for it to be a solution. If water is one of the substances, we call it an aqueous solution. Solute is whatever's being dissolved, and the solvent is whatever's doing the dissolving. Water is about the only one we'll use in here for that. Water is a great solvent. Y'all know you can take salt, pour it in a glass, pour water on top of it, and what happens to the salt? It dissolves, right? Can you put sugar in your tea and make sweet tea? Does that sugar dissolve?
No.
Absolutely. No. That means you're putting too much sugar in there, right? So, cold brew versus hot brew. Which one dissolves the sugar faster? The hot. Based off what we just talked about with water, what do you think is happening there?
It's heated up.
It's heating up. Very good. It's heating up, right? When water goes in to dissolve something, like what they're trying to show you here. When water goes in to be the dissolving agent, whether it's salt or sugar or whatever it is, water having charges on it, being a polar compound, is what allows it to dissolve stuff. So the positive sides of the hydrogen, the negative sides of the oxygen, take sodium chloride, for example, which is table salt. The negative oxygens will come and pull on the positive sodiums. The positive hydrogens will pull on the negative chlorines and they separate them. The water molecule separates the sodium and chlorine. And that's what it means to dissolve salt. So if you have salt in the bottom of a glass and you pour water in on top of it, those water molecules start plucking the sodiums and chlorines apart. Well, let's say that was sugar and we're doing tea. If you have cold tea, basically those water molecules are being lazy, right? They're cold, they're not energized, they've lost their energy, right? They've cooled off, they've lost their energy, and they're in no hurry to move at all and get down in there and separate out those sugar molecules from each other and dissolve that. They will eventually get to it, but it takes longer, right? You gotta stir it a little bit more and kind of whip them about, but they eventually do. Now, if you have hot tea and you put sugar in it, what does it mean that that tea is hot? What has happened to those water molecules? You said it, Brittany. They're energized, right? We've heated them. We've given them energy, and they are whipped into shape, and they get in there and they start separating out all that sugar, and they dissolve it much faster. It's not better, right? It doesn't make them do it better, but it makes them do it faster. Now, there's something in chemistry called supersaturation, where you can force molecules to absorb more than what they should, and that's not what we're doing here. But is there a limit to this, right? If you pour half a glass of sugar, half a glass of water, what's going to happen there? Is all that sugar going to be dissolved? No, there's a limit. There's only so many water molecules, and once they've all picked off their sodium chloride or their sugar and separated out, there's nobody else left to grab what's left. So there's a limit to that. There's a limit. Aqueous solutions. so the ones that have water in them. These are some terms that we throw about with that as well. And these will get used in here, the hydrophilic, hydrophobic, amphipathic. You'll have had these before, right? And we're taught these from a very small age. That hydrophilic means water loving, and hydrophobic means water fearing. And amphipathic we're probably not taught about as much. Amphipathic means you have a molecule that is both hydrophilic and hydrophobic. So it may have a hydrophobic area over here and a hydrophilic area over here. Do y'all remember talking about phospholipids in the cell membrane? They're amphipathic. They have those hydrophilic heads and those hydrophobic tails. That's great, right? That we're taught water fearing, water loving, but what does that actually mean? What does it mean that something is hydrophilic or hydrophobic? Now, your book says that it means that hydrophilic means it'll dissolve in water, hydrophobic means it repels water. Well, what does that even mean? For something to be hydrophilic, it has to have a charge. The fact that it loves water means that it actually means that it attracts water. And the only way to attract a water molecule is with a charge. Because water molecules have charges on them, right? The oxygen is slightly negative, the hydrogen is slightly positive. So in order for something to attract water, it also has to have a charge on it. So if you have something that does not have a charge, then it is not going to be attracted to the water. And it's not necessarily repelling it, but it's not going to be able to be dissolved by the water. In order for water to dissolve something, that something has to have a charge so that water can grab on be attracted to that charge and separate it. And if something doesn't have a charge, water will be all around it, but it's never going to penetrate through. It's never going to be attracted to that. Okay, pH, and then we'll stop, right? pH, and then we'll stop. pH is something that I know y'all are taught in both biology and A&P. Should be a refresher, right? Let's go back over pH though. pH is something that we get from water. When water breaks down, we get things that make pH. So you've got some ions here. When water breaks down, right, water is H2O. When water breaks down, it will break down into one single hydrogen ion and a hydroxide ion. Now, the H, the hydrogen, has a positive charge. What has happened to a hydrogen to give it a positive charge?
It lost its electrons.
Yes, it lost an electron, right? So it's got a positive charge now. So when water separates, the electrons don't separate right. Hydrogen, one of this hydrogen's electrons, it's only an electron, will actually go be part of this hydroxide. And so the hydroxide, since it's got an extra electron, now has a negative charge. So the electrons don't separate right. But this is what gives us pH. Hydrogen ions are responsible for acidity. Hydrogen ions are responsible for acidity. Whereas the hydroxide ions are responsible for alkalinity, which is being more of a base, right? Making something more basic, but the real word there is alkalinity. So hydrogen ions are responsible for acidity. Hydroxide ions are responsible for alkalinity. It's great. But again, how do we apply this? How do we actually understand what this means? Well, as people, we've come up with a scale, right? pH, we have a pH scale that goes from 0, which is the most acidic, all the way to 14, which is the most alkaline, or the most basic. 7's neutral, right? 7 is your neutral pH. What this pH scale actually is referring to is the concentration of hydrogen ions compared to hydroxide ions. That's what it's actually referring to. If you have a beaker, I'm going to draw y'all 3 beakers here. 3 beakers. Let's do the top beaker. Let's say that you have a beaker that has 6 hydrogen ions, 4 hydroxide ions. So if this is what's in your beaker, and you do a count, you have 6 hydrogen ions, 4 hydroxide ions, whichever one you have more of determines whether you have an acid or a base. We have more hydrogen ions, so this is an acid. And the more hydrogen ions you have, the more acidic it is. So let's say I had this beaker, and I had, I'm just going to do numbers instead of writing them out, 5 hydrogen ions and 5 hydroxide ions. What would you call this? Neutral, right? This one's neutral. Equal amounts of hydrogen and hydroxide ions is a neutral pH. Whereas if you had 2 hydrogen ions, 8 hydroxide ions, you would have a base, right? You would have a base. The more hydroxide ions you get, the more alkaline or the more basic it becomes. Really, most people who study this will focus on the hydrogen ions, and they say, well, if you have more hydrogen ions, it's an acid. If you have fewer hydrogen ions, it's a base. We know that they change in relation to each other. Notice I've kept my number adding up to 10 every time. If one goes up, the other goes down. Very much like absorbance and transmittance, right? If one goes up, the other one goes down. And they always change with each other. The pH scale is a logarithmic scale. What that means is that each unit change in pH is a change by a factor of 10. So if I were to ask you, how much more acidic is a pH of 1 than a pH of 2, what would you say? Every unit change is a change by a factor of 10. It's not a trick question. It's as easy as it sounds. How much more acidic is a pH of 1 compared to a pH of 2? 10 times. What that actually means is that there's 10 times more hydrogen ions here than there are here, is what that actually means. Something with a pH of 1 would have 10 times more hydrogen ions than something with a pH of 2. Now, what about if I asked how much more acidic is a pH of 1 compared to a pH of 3? What would you say?
25.
Ooh, very
100,
close,
30,
right?
30.
Changing by a factor of 10 means you have to multiply instead of add. So it would be 10 times 10 instead of adding, right? So it would be 100, not 20. Everybody see that? So what would, so you go 10 times 10. That means that a pH of 1 is 100 times more acidic, has 100 times more hydrogen ions than something with a pH of 3. What about if I asked you how much more alkaline something with a pH of 13 is compared to a pH of 10? What would you say?
1,000.
1,000, right? 10 times 10 times 10. Okay, I feel like you got pH. We use pH in here, again, with our microbes, because we study how pH affects them. Because what we find is that if people don't eat right, if they don't drink right, and they change their pH, women, we have a problem with this, right? We get yeast infections because we drink too much sweet tea, or it's that time of the month, or whatever the case may be, and our pH changes. And a microbe that normally wouldn't have been able to grow there is now able to grow. And kids in the mouth, right? They were giving your kid antibiotics, or maybe some of you have, took a round of antibiotics, and you get a thrush infection from that. That is a fungal infection. And it's because the pH in the mouth has changed, and now a fungi that wasn't supposed to be able to grow there now can, because the antibiotic changed that. So pH is an important one. Okay, we'll stop there. And we'll pick this back up on